Hello and welcome back to sections 20.1 through 20.4. In this video we'll be doing a example 2, which will look at rotation about a fixed point. So last time we looked at general plane motion and how we can simplify that if we assume that our vector from A to B or whatever is constant in magnitude. This is a further simplification. If I can treat all rotation as if it goes about a point, then it's basically as if I have some fixed length rod touching the edge of a sphere, and so I'm just modeling where on the edge of the sphere is it. So the first thing we need to do is we need to talk about the difference between finite and infinitesimal rotations. And then we'll develop equations for velocity and acceleration. And then finally we'll apply those to this example 2. Alright, so for finite rotations, we talked about this previously. If I take two things and I rotate them the same amount but in different orders, so say I'm going to rotate about this axis and then this axis for this one. I'll just do 90 degrees since it's easy. So if I go 90 degrees about this axis and then 90 degrees about this axis, I end up in this orientation. Let me slide that down. Now if I do the same thing but I go in the other order, this time I go down here and then I go over here. So if I rotate, so they start in the same orientation. Let's prove it. So same orientation, go forward, go left. In this case we'll go left and then we'll go forward. So we notice that they end up in different final orientations. That's because finite rotations are not vectors. They don't just add up and end up in the same point. But if I undo this, if I make those rotations very, very small, so again, I'll go forward for just a little bit and then up for just a little bit. You probably can't see it. And now I'll go up for just a little bit and forward for just a little bit. They start to become very, very, very similar in location. And if I make these small enough, they'll actually be at the same location still, if I use infinitesimally small rotations. So basically what we're saying here is theta 1 plus theta 2 does not equal theta 2 plus theta 1. However, d theta 1 plus d theta 2 does equal d theta 2 plus d theta 1. Because they're so small, we still end up in the same orientation. And this is a good thing. This means that something that uses this, such as angular velocity, so I might have some d theta 1 dt plus d theta 2 dt. Well, that's just, I can treat these as vectors, and those vectors are the same thing as saying omega 1 plus omega 2. I can expand this. I can find the resultant omega vector, and that will be some omega 1 plus some omega 2 plus whatever. They're just vectors at this point. So I can add them up because they contain these thetas. Now, the direction of that is the instantaneous axis of rotation. And this is useful later on. We'll look at this in example 3, how we can apply this. The direction of this. Now, if I want to find the angular acceleration, I first need to go, and in the book it shows you the proof for this, so I'm not going to prove it here. But if I have any vector in the translating and rotating frame, the time derivative of it, so this is any vector, so a lot of times you're going to use this for velocities, but you can also use it for omegas. Well, the general form is that that vector A, its time derivative is equal to the time derivative of that vector in that local coordinate system, so x, y, z, plus the, so again this might be like, oh, I'm trying to look for acceleration, so it's the local acceleration plus something. So this is going to be the rotation of the rotating coordinate. So again, this isn't the translating and rotating frame. Sorry, that's probably not showing up for a TR frame. So translating and rotating is what that stands for. And we're going to cross that with our original vector A. So what this means for this, so alpha, well, this is just omega dot. And I can find that by looking for the omega dot in the local coordinate system. So if I have some local accelerations, and then also doing a cross product with the rotation of the coordinate system. And so this will make sense when we come down to example 2, hopefully. Cross it with omega. And the neat thing that happens, if I have constant angular velocity, but the coordinate system is rotating, I still get an acceleration even if the acceleration, like the stated acceleration, is 0. So if I say that, oh, these are constant, well, constant angular velocities can give me angular accelerations if they are rotating, like if there's a rotation in the coordinate system. That's what this means. So let's look at example 2, and we'll apply these equations. So I'll go back to the picture real quick so you can see what it looks like. So we have this fan. This fan is spinning about 2 different axes. So you've probably done this before. You pull up the button or whatever, and then it'll sit there and oscillate about this axis. But the fan blade is spinning about this axis, and this axis is 45 degrees off of the y-axis. The local system A down here, you can't see that, shares a point with B. We will always be rotating. So basically what we're doing is we have this point out here. You might call it point B. This is going to trace the outside of a sphere if I let it. So this is an example of a vector. So our vector omega s here is tracing around with a fixed point at A, or O, whichever one you care. It's the same point in this case. Alright, so let's do that. So we're trying to find omega. So we know that our omega vector is just the addition of the vectors in here. So it's just going to be this omega z and this omega s because those are vectors. So we're going to get omega z. Omega z acts about the z-axis. Again, use right-hand rule. You'll see that it's positive k. So we want to turn it into a vector. This is just a magnitude initially. And then we're going to add that with this other vector, omega s. And that's going to be, based on this 45 degrees, it's going to be split up into partially in the y direction, partially in the z direction. So let me multiply that by a vector. So there's no parts of this in the x direction. There is, so it's 45 degrees, which means that I have a 1, 1, root 2 triangle. That's what a 45 degree is. So if you wonder where these root 2's are coming from, that's where it is. So I'm going to get 1 over root 2 in the y direction, and that is positive. And I'm going to get 1 over root 2 in the z direction, and that is also positive. And I'm going to double check that this is a positive. So again, point your thumb in the positive direction of omega x. See if your fingers rotate the same direction as it's indicated. If it is, then it is positive in the s direction. So we're good there. So now we just clean this up. Omega z is 1. Omega s is 60. So I will get nothing in the I direction. This is just a dot product. I'm just basically distributing this out. In the j direction, we're going to get 60 divided by root 2. And then in the z direction, we're going to get 60 divided by root 2 plus 1. And let me calculate that in a fraction, sorry, in a decimal form. Alright, there you go. So 0, 42.43, and 43.43 radians per second, all positive. And if you don't want to use the root 2's, you could just use cosine 45 and sine 45 would also work there. So that's omega, but I also want to find alpha. So let's go find alpha. Alpha, we know, is going to be equal to omega dot in the local coordinate system plus the rotation of the coordinate system crossed with omega. Well, I already know omega, so I can put that in. These are all constant accelerations. Constant, so this will zero out. So the only question is, what is this? This is our 0, 42.43, 43.43. So that's that. So what is big omega? What is the rotation of the coordinate system? So if we go back and look at this, you can think of it as the following. Actually, I think an actual model will look better. So let's go back over here. So we have our fan. So let me kind of tilt this so you can see it. So we have a makeshift fan here. It spins about its axis. And then this fan, so it's rotating about the z for the oscillation. So that's the rotation of the coordinate system. So this red coordinate system is that rotating coordinate system. And inside of that coordinate system is the fan that spins. So what we want to do is treat this as just this component. So this would be our rotation of the coordinate system. If I had a coordinate system that if we have a top view, then we might have, say, x coming down, big X going down, and big Y going down. And then initially, little y, so maybe y1 will be right here. And then sometime later, we're going to rotate this thing. And so at y2, we're going to be some direction this way. Think of it that way as well. So we're going to use our omega z. So we're going to use our 1k hat here. So then we just do the cross product here. So let me just rewrite it so you can see what we're doing. So we have 1k hat. We're going to cross that with 0, 42.43, and 43.43. Make our little diagram here, I, J, K, so we can do our cross products really quickly. So we're going to have a k hat with a 0, so that's going to do nothing. So that's a k into an I, which is going to be our j hat. So we're going to get a 0 here, so that and that goes there. You can't see that. There we go. That's better. So k into I makes a j. K into j makes an I, so it's going to be here. So we're going to get a 42.43. That's just 1 times that. But we went k into j, so it's actually negative. It's a negative I hat. Because I went from k crossed into j, and I got my I. And then k crossed with k is 0. So anything crosses with the same direction doesn't produce a torque or a moment, if you remember from that. So same thing with these. So that's going to be our answer, radians per second squared. So negative 42.43 I hat, radians per second squared. That is our alpha vector. All right. So hopefully that helps. If you have any questions, feel free to reach out.